All right, so this is a cumulative quiz review for everything quiz 4 material. I didn't do one of those super long titration problems I've done the last two past sessions. So if you want like any more practice with titrations, I would probably go look at the recordings from my last two sessions. There is one on this, but it's not going to be like step by step every step of the way in a titration, if that makes sense. So I wanted to focus more on the stuff you did last week. Um, Specifically KSP solubility. You're going to see a little bit more of that than I'm guessing what you're going to see from the Friday stuff of like common ion effect. But be familiar with all that stuff. I do have one. I think at the very end, I have like a common ion problem. So we can talk about that. I know that that was kind of tricky for a lot of people on Friday. And then, as always, if there's something that I don't talk about in this session, I'll stay after for a few minutes. So you can ask me then. But let's get started with the, that's better. Um, Molar solubility and KSP stuff. So we were told that when you put a salt into water, it has a molar solubility that's kind of based off of its equilibrium expression. So we can talk about these salts turning into their separate ions as an equilibrium constant. So yet another one of those capital Ks. This one's KSP, so solubility product constant. And this first example, we're using the salt silver chloride. And so we're going to see how that breaks apart into the two separate ions, and I gave you a KSP of 1.77 times 10 to the negative 10. So using that, we can calculate the solubility, also called the molar solubility. Those two things mean the same thing. So do that first. Try to calculate the molar solubility of silver chloride. And then we're going to talk a little bit. Oh, here we go. I didn't even notice. There is a common ion effect in this one. So we'll talk about common ion, how that impacts solubility. And then, yeah, spend a few minutes working on this first one, and then I'll go over it up here. For those of you guys coming in right now, we haven't really started anything yet. If you want to fill out the attendance form first, and then we're working on the very first one. Yep. Can everyone in the back see the board okay? All right, so I'll start working through this first one. Not too bad, right? So we have silver chloride. It's kind of a normal salt. It doesn't have a whole lot of coefficients or anything. It's going to break up into straight up one silver and one chloride. So not a lot of tricky math there. And we're going to see that when you're doing this molar solubility stuff, you can either use an X as your variable, or sometimes I think Dr. Gormley will do an S. So I'll use an S here. If we were doing an ice table, you can imagine we would do like plus S, and then in the equilibrium, right? So we have like the whole ICE stuff. It'd be S and S, and there's no coefficient, so we don't need to square anything. We don't need to multiply anything by two or whatever. So in this one, the KSP is straight up going to be S times S, or S squared. And if we're given the KSP, then we can solve for S. That's the molar solubility. So let's do that. It's 1.77 times 10 to the negative 10 is equal to S squared. So we're going to take the square root of both sides. I'll do that real quick. And we get a molar solubility of 1.33 times 10 to the negative 5 molarity. So yeah, the solubility is in units of molarity. KSP is a unitless thing that's like any other equilibrium constant. So now this is good. This is some common ion effect we'll practice on the next couple. So this next one, we don't need to do any math. It's more of a conceptual one. If we added NaCl, sodium chloride, into the solution, do we think this would increase, decrease, or do nothing to the solubility of that first salt that we had, the silver chloride? What would decrease? Yeah. Do you want to explain why?
Chloride ion, so that it's going to shift the equilibrium to the left.
Exactly. Yep. So all of these common ion effects are straight up Le Chatelier's principle problems, which you already learned last unit, but now we're putting it into, more real practice. So like you said, exactly, we have NaCl. It's a solid. It would break up into sodium ions and chloride ions. And if we're increasing chloride, we can think about this first equilibrium expression. We're increasing one of the products. We said that in Le Chatelier's principle, if we increase products, we're going to shift to the reactants to make more of the reactants, right? It's like a balance beam. If we add one thing to another side, it's going to try to do the opposite to get it back to balance. So if we add more chloride, it's going to go to the left side. Basically, it's going to start spitting out more and more of the solid. We're decreasing the solubility of this salt. Is that good for everyone? Cool. All right, now this is another type of common ion effect problem you could see on the test. This time we do have to do some math. So it's saying if we started with, or if we added specifically 0.1 molarity of sodium chloride, what would the new molar solubility be of silver chloride? So spend a few minutes working on this one. Another problem that totally reasonable to see on your test. So make sure you're comfortable with this. So I'll kind of show this one up here. Really not a tricky problem. Try not to overcomplicate it. What we're doing now is we have a molarity of the sodium chloride, and we know it's a 1-to-1 ratio, so we don't need to do any math with it, right? One chloride ion is produced for every one molecule of sodium chloride. And so what we can do there is we can put that molarity in to this initial KSP equation that we did up here. So again, to bring it back to ice tables and what we're really comfortable with, in the ICE, we know that if we had an initial concentration of 0.1, it would really be like 0.1 plus S. And so then we would have 0.1 plus S at equilibrium, right, as review. And we have a KSP that's really small. It's times 10 to the negative 10. So we can get rid of the plus S here. So really, our KSP equation now for finding the molar solubility is KSP equals S times 0.1. And all we got to do there is divide both sides by the 0.1. And so we're going to see that the molar solubility of silver chloride becomes 1.77 times 10 to the negative 9. Is that okay for everyone? And also, let's make sure that our second answer was right. Is this less than this? It is. So this is a good way of like mathematically showing that, yeah, we're decreasing the solubility by a lot, honestly, by increasing or by adding sodium chloride. Yeah, all I did was divide by the 0.1 on both sides. Cool. All right. I think honestly, that's a more realistic example of common ion effect that you'd see on your quiz. Some of the stuff on active on Friday was pretty tough. That stuff takes me a few seconds to do also. So if you're good with this, you should be in a good spot. Let's do some more of the solubility stuff though. So this one honestly might be a bit easier. Write the balanced dissociation equation for barium phosphate. So this is going back to Chem 131 a little bit. We need to know our polyatomic ions. Hopefully you remember what phosphate is. And then from there, once we've balanced that chemical equation, we can do another one of these solubility types of problems. So see if you can do this one on your own. If you need to look up a periodic table, that's totally fine. Barium is in the second row, so it's going to have a 2 plus. Start working through the rest of this one. So if you didn't know, this is how we're going to write barium phosphate. Right, barium has a 2 plus phosphate polyatomic ion, PO4 3 minus. Can you guys see this okay? All right, perfect. And so the dissolution equation, or whatever we want to call it, is going to be this turning into 3 barium 2 plus ions and 2 PO4 3 minus ions. So it's a very quick 131 review. The basically the superscript here, the 3 and 2, is going to be kind of like flipped. So the phosphate is going to get a 2 in the subscript, and the barium is going to get a 3 in the subscript. If you need help with that, stick after. I'd be happy to work one-on-one with you. But yeah, so we do the like normal ice table stuff. It would be plus 3s and plus 2s, s for solubility. And KSP we set up like we've been doing K expressions for like 2 months now. And so the 3s is our equilibrium part. So that's obviously going to go into these brackets. And so we're going to have 3s cubed times 2s squared. And this is where I make the mistake almost every semester. 3 to the power of 3 is 27, not 9. So it's 27s cubed times 4s squared. 27 times 4 is 108. So this is really 108s to the fifth. This is like probably the biggest type of problem you'd get like this, 108 s to the fifth. And so now we have the thing that we need. We solve for s, and we know that KSP is 6 times 10 to the negative 39. So I'm going to divide this number by 108 and then take the, I don't even know what that's called, 1 to the fifth root or something like that. And if you're curious how I do that on my calculator, so I'd first do 6 times 10 to the negative 39, divide by 108. And then I do it by using that caret button and then putting in parentheses 1 divided by 5. So 8.90, I guess, times 10 to the negative 9. Molarity, that's going to be our molar solubility on this problem. Do we feel okay with that? Awesome. All right, now a little bit more conceptual. This is, a definition that you got to memorize. You have to know what a buffer is. We talked about buffers the entire unit. That's what the BCA tables are based off of. Does somebody want to quickly say what 2 things need to be intact for a buffer? Or like what you need for the components of a buffer to be are? Mhm. Exactly. So they need to be conjugates and they need to be weak. So how about this first example here? Do we think this makes up a buffer? Yes. CH3COOH, that is acetic acid, that's a weak acid. And then its conjugate is also, that's a weak base. And we know that this is the base because it has one less H and it has sodium there to balance it out. So sodium is like a counter ion here. We don't really care about it. What about the next example? No. In this case, it looks like they're conjugates, yeah, but there is a big problem, and that's that HCl is a strong acid, so it couldn't work. How about the next one? Do you think that could be a buffer? Yeah, we have ammonia and ammonium. Those are weak, and they're separated by one proton. So again, conjugate pairs. So A and C, so far we can say they are buffers. And how about this last one? It's maybe a little bit trickier. This one is a buffer, yeah. So we have HCO3 being the acid in the first one. That's a weak acid. And then CO3 with one less H in the next example. So the only one of these that wouldn't be a buffer is B. Do we feel good with that? Nice. All right, now let's put some of this buffer stuff to use and do one of the BCA tables that we've been doing for a while. So in this one, this is a straight up BCA table. We don't need to do anything too crazy here. So spend a few minutes working on this one and see if you can find the pH of the system. All right, what equation are we using in this one? Henderson-Hasselbalch. Yep. So this is how I'm solving this one. Again, anytime we're doing one of these reactions, any type of titration problem at all, we need to be using units of moles. Concentration does not work for like determining what we've reacted away. So again, as a quick review, you always multiply the volume in liters by the molarity to cancel out the volume unit, and you're left with moles. So that's what I did here. I didn't show my work for the KOH, but we know KOH is what? It's a strong base. So we have a strong base reacting with whatever this is. I mean, it looks like it might be an acid. We have a proton sitting here. It's definitely not a strong acid, though. We know that. And so we set the BCA table up with our mole values. We're starting with none of the conjugate base. And you always subtract by the smaller value in a BCA table. So we have a little bit less OH minus than our weak acid. So we subtract all of the we subtract all of the strong base away, and that's what we're adding to form our conjugate base, right? And now once we have this, we have both components of the buffer after doing the BCA table. That's our indicator that we can go straight into Henderson-Hasselbalch. No ice tables, none of that stuff. So kind of a nicer problem. Um, and Henderson-Hasselbalch again is pH equals pKa. We have the Ka, so we're going to do negative log of the Ka plus log of what over what? Bases over acid. Yep, so base is going to be our 0.0028. Make sure you don't mess up this part. I'm sure on his test, he'll have one option where it's like the numerator and denominator are flipped, and that'll be the wrong one. So that's a very easy spot to like mess up your points. Make sure you're always doing base over acid here for Henderson-Hasselbalch. So let's do that in our calculator. So again, quick review of buffers. The entire point of them is that you can do these types of reactions, and as long as you don't go out of the buffering capacity, your pH is not going to be too different from what it started as. So right, we went pKa of 5.23. We've added the strong base, but it's only going up to 5.47. So it's not too big of a difference. Yeah.
Um, I don't know, it's a question you can apply it, but would you have to add the new volume and then get the concentration of the weak acid and weak base with the new volume?
It's a good question. No. So think about it this way. If we found the new volume, both of these are in the same solution, so they'd both be divided by the same value. And so as a ratio, it wouldn't make any difference. So I always use moles when I'm doing my Henderson-Hasselbalch here because it would be a waste of time to turn it to molarity. You get the same answer, but it wouldn't do anything mathematically.
You wouldn't have to do like 0.02 meters plus 0.014 meters.
Yeah, and the times when we do that are going to be if we only had our conjugate base left. So I don't have an example of that on this past session. The last two I have done that. But when we think of the equivalence point, that's when we fully react away our starting amount, right? So we'd be left with 0 here and a 0 here, and we would only have something here. We can't go into Henderson-Hasselbalch at that point because then we'd have something over 0. You can't put a 0 into Henderson-Hasselbalch. So we would have to then turn this from moles into molarity, and that's when we would need that new total volume. And then from there, we would do an ice table, and that's how we find pH. But yeah, if you want more practice with titrations, look at the videos of the last two past sessions. But here we got one that is a strong acid, strong base titration. Has he done one of these with you guys? Okay, cool. So this is maybe the most simple type of titration. We have sodium hydroxide being titrated with nitric acid. And I want you to first calculate the pH before we've added any of the nitric acid. And then do this, calculate the pH after 35 mils, and then find the pH at the equivalence point. Anyone get a pH yet? Yeah, right about. I got 13.18. So this one, really simple. Before we've added anything, we have a strong base. And if you remember from last unit, anytime we have a strong acid or a strong base, those ones fully break up into their two separate ions. So it's not an equilibrium arrow. It's only a forward arrow. And we have to make sure that it balances 1 to 1. And it does. So for every 1 sodium hydroxide, we're making 1 mole of hydroxide. And so all we have to do is do negative log of the molarity, and we get POH, and then 14 minus that, and I got 13.18. So not too bad. But now do it after we've added a little bit of nitric acid. Anyone get a pH for this one? Mhm. Yep. So this is an example, like we were talking about, where you do need to calculate the total volume. Now I'll show my work here. Right, we're doing a BCA table as normal. And again, I think the strong acid, strong base titrations are a little bit easier than the strong acid, weak base or strong base, weak acid. But again, this is what our BCA table setup looks like. Um, we're always using moles in BCA tables. So that's what I'm doing here. And then again, we're always subtracting by the smaller value. So we end up with nothing left of our protons, and we have a little bit of the hydroxide left over, right? We got 0.0005 moles of hydroxide after the BCA table. And now if we have moles, we know we can get molarity. And once we have molarity of hydroxide, we can once again do negative log of that and get POH. So we're going to set up the concentration as 0.005 moles, 0.0005 moles over the total volume. So that's going to be the 50 milliliters of our sodium hydroxide plus the 35 milliliters that we added of the strong acid. That gets us our concentration of hydroxide, negative log of it. We get 2.23 as a POH. 14 minus that is going to be our pH. Anyone have any questions with this one? Cool. All right, next one. I'm going to save you the possible headache. You don't need to do any math on this one. What is the pH at the equivalence point? 7. Awesome. Yeah, totally could see that being a conceptual problem on your test tomorrow. Strong acid, strong base titrations always are perfectly neutral at the equivalence point. All right. Another one of these K-space. I threw a lot. Well, I threw a lot in here. Okay. Um, if the molar solubility of Ag2S is 5.4 times 10 to the negative 17, what is the KSP? So this is kind of like the inverse of those other problems we were doing. Now we're given the solubility and we're asked to solve for the KSP. So spend a few minutes working on this one. Anyone get an answer for this one? Did not get that answer.
The -49.
That's what I got. Right. So for these ones, it does always throw me for a loop doing the inverse. I feel like getting KSP from or getting molar solubility from KSP clicks a little bit better in my brain. I kind of have to work backwards to do these types of problems, but it's really nothing too bad. So we're doing, again, break this salt into the two separate ions, set up the KSP expression, and then once we've set that up, we know what S is because that's our molar solubility. So we plug that in. And again, always do PEMDAS. We're doing parentheses, exponents first. And we're going to do the solubility to the power of 3 or anything else, and then multiply that by 4. And that gets us KSP. And it is very common for these KSPs to be super tiny numbers, like times 10 to the -50, -60, stuff like that. So don't get an answer like this and feel like, oh my God, I definitely did something wrong. Because this, in this case, is the right answer. Anyone have any questions about this? Okay. Next one is a little bit more involved, a little bit of a trickier one of these KSP ones because I'm actually asking you to go a step further and find the pH after being given the KSP of one of these expressions. So if this is throwing you for a loop, think about what we've done so far and try to connect this process back to like what we know about ice tables and what we know about finding pH from, getting that X value that we're solving for. Kind of my hint for this one. I'll start working on this one with you guys. So again, don't look at it too different from these other KSP problems we've done. We still have this thing that we're dropping into water. It's going to break up into the two separate ions. And we know that this is going to balance into Fe3 plus and 3 hydroxide ions. And so if we were doing an ice table, we would do plus X plus 3X, X, 3X at equilibrium. And then from there, we can use that KSP to solve for solubility. So again, it's going to be X here, and then 3X is getting cubed. So it's going to be X times 27X cubed. So really 27X to the 4. Divide this by 27, take the 143 or whatever you want to say, and that gets us solubility. So that is nothing new so far. Now the next step though is we have to find pH. Does anyone have a guess of how we can do that?
Find the concentration of OH ion reacts and then find POP. So find
Exactly, right? So if we have OH minus here, we have X, we got to plug it into the equilibrium concentration of OH minus. Then we can do negative log of that, get POH. So 3 times X is 3 times this. That's 5.89 times 10 to the negative 10. And so this is our concentration of hydroxide at equilibrium. So we can do negative log of that number. And I get a pOH of 9.23. So pH of 4.77. Is that okay for everyone? Could totally also see like this exact kind of problem being on your test tomorrow. This is conceptual. Define what happens. So again, we've talked about Q and K for a while now. K is when we're at equilibrium. We know that for a fact. Q is when we're at any conditions otherwise. It could be at equilibrium, it could be before equilibrium, it could be after. And it's good to know what happens to the solution when we're at these different points. So what do we think happens if QSP is less than KSP? How can we define that solution? Use the terms like saturated, unsaturated, supersaturated. That's kind of what I'm getting at here. Unsaturated. Yep. If QSP is less than KSP, that means we still have some room to go. We can keep dissolving more and more ions. And so we would call it unsaturated. If QSP is equal to KSP, we're at equilibrium, we're saturated. That means we're at the exact amount of ions that we would consider equilibrium with this KSP value. And anything past that, so if we had QSP greater than KSP, that would be called supersaturated. And that's something that you can really only do in like a lab setting, as far as I know. So it'd be like maybe you really heat up the solution or something and you can dissolve a few more particles in there. But it's possible he could give you something where he gives you like real values for QSP and you have to solve KSP. And then he asks like, will it keep dissolving? Are we saturated? Are we supersaturated? So make sure you know the relationship here. Saturated. Yep. All right, last one. This is, I think, yeah, some more common ion effect stuff. So we have an endothermic salt, or an endothermic dissolution of a salt, meaning it requires heat for us to dissolve this thing, right? And it's ammonium chloride. So I'm asking, if we had ammonium chloride sitting in water, we know some of it's going to dissolve. It'll be at equilibrium. And I'm wondering what would increasing the pH do to the solubility of this salt? So this is the thing that on Friday was really tripping a lot of people up, myself included. So don't worry if it's hard. But see if hopefully you figured it out on Friday. Spend a few minutes working on this. And again, like all common ion effect things, Le Chatelier's principle is kind of the main way you have to solve this problem. right, anyone have an answer for this one? You were thinking it would decrease solubility. I'm thinking this would increase the solubility of the solution. So let's break this down. Right, we have our salt here that we're curious about, NH4Cl. I want to make sure I didn't mess anything up here, but we're breaking it up into two separate ions, right? So we have an ammonium ion and a chloride ion. And we're asked about how would increasing pH affect solubility. So increasing pH means we're getting more hydroxide ions and less hydronium ions, right? Nothing surprising there. But we want to see how these two separate ions behave in water, right? So we know that the pluses go with the minuses. So the plus in the ammonium is going to go with the minus, the OH minus, to form NH4OH. And is this a strong base? No. So that means that it really will form some of this, right? We will be at equilibrium. This will happen. But then we would see that the Cl minus, we would see it, okay, minus goes with plus. We could try it out, but what is wrong with this? We're forming a strong acid, right? So if we're forming a strong acid, that means this really won't be at equilibrium. It would only break up into the two separate ions. So this is not really an equation that we care about. So the only thing that is really interacting with these ions is the NH4 plus. And if we're increasing the pH and adding more and more OH minus, what does Le Chatelier's principle say is going to happen here? It's going to go to the products, right? If we're increasing the reactant here, we're going to make more of this. And if we're making more of this, well, we're reacting away more and more and more of this ammonium ion, right? So if we're reacting this away, let's go back to the first equation, the one we really care about. We're decreasing the ammonium concentration. So now what does Le Chatelier's principles say is going to happen here? Also going to move to the right. Yeah. This one is going to start going over here. And that's really our answer, right? If we're going over to this side of the equation more and more, we're breaking that salt up into the two separate ions more and more frequently. So we're increasing the solubility of this. That's how you have to look at these problems. Yeah. Like, how do I know that this is going to mix with this part of the water?
Yeah. That was what tripped me up too. I thought it was gonna act as a conjugate acid and release the H plus.
I see what you're thinking.
Is it just because it has like such a low value that the H, like the OH that are already there, just have a higher chance of interacting?
So like in reality, it probably is doing a little bit of that. It might be releasing a little bit of proton. I wouldn't think about that. The way you have to do these problems is see what component, hydroxide or hydronium, in the water is reacting with those two separate ions. So don't think about this in the sense of like what it's going to do as an acid or base. Think of what it's mixing with in the water. That's my best advice for this type of problem. I get what you're saying, but yeah, this is what you got to do here. Yeah.
Should we just like combine it all the time and just literally combine the anion and the cation?
Yep.
That's gonna be.
Plus goes with minus, exactly. So this is exactly how I would do this on your test. And you would do a Le Chatelier's here and see then what's going to happen to the big one, the equation that we really care about. And if it's going to the right, that means we're increasing the solubility. And then next one, how would decreasing temperature affect solubility? So again, I said this is endothermic. Yep, exactly. So if it's endothermic, we learned last unit that you can almost write the enthalpy as a reactant, right? We can think of this as a necessary thing that needs to be in the reactants for the reaction to occur. And if we decrease the temperature, think about like lowering this thing right here. Le Chatelier's principle says that this is gonna overall shift to the left side. And if we're shifting to the side of the solid, that means we're decreasing its solubility. Yeah, this stuff is tricky. It takes practice. I would do it this way. Honestly, maybe like ask AI if it's confusing, see if they have a good explanation. This is my most simple way of explaining it, but every semester I kind of struggle with this one too. But yeah, if you have any questions about this, other titrations, whatever, stick around. Also, if you got in a little bit late and didn't do the attendance, I would appreciate it if you could.